Hey, everybody. Okay, so we are going to end this class at the beginning. What do we understand about the Big Bang and the very early universe that eventually evolved and turned into the one that we live in today? What do we know about the Big Bang and how? Why do we know it? Right? Where does this idea come from? What are the major pieces of evidence that lead us to conclude that our universe began in this event that we call the Big Bang? Well, we talked about one before, right? The Hubble expansion. That if the universe is expanding and getting bigger and bigger and bigger, then that means that in the past, the universe must have been smaller. And before that, it was even smaller. And before that, it was even smaller. And then at the very beginning, the universe must have started at with a place, or not with a place, because it was the whole universe. It was every place. The universe began such that all points in space were at the same point in space, and the universe would have been infinitesimally small, infinitely hot, and infinitely dense. Right? Because what happens to matter and gas and energy? When you compress it, it heats up. And if you compress it even smaller, it heats up even more. And if you compress the entire universe into an infinitesimally small point, a single point, then what was the universe like? To that, there is not a terribly satisfying answer because everything goes to infinity. Right? The problem with taking the universe and shrinking it down to being infinitely small is that the answers to all the questions end up being some kind of infinity, right? That the universe would have been infinitely hot and infinitely dense. And what does that even mean? Not a lot. This original idea, the idea for the Big Bang, came from Georges Lemaitre, who was a Jesuit priest and an astronomer. And so when Hubble and his contemporaries were presenting the evidence for the redshift of galaxies, Lemaitre sort of took it to that logical conclusion and said, well, okay, then the universe must have started out infinitely small, infinitely dense, infinitely hot, and then the expansion of space started, and all points in space started expanding away from each other, and they still are today. This idea of a universe that started out tiny and then expansion started is what we today call the Big Bang Theory. The problem the problem with figuring out all the logical questions about what caused the Big Bang Theory, what was the universe like right at the Big Bang, how did this all happen? Our current understanding of physics doesn't answer that question because everything was infinite, right? Math, right? Our understanding of physics is based on, math and predictions and what we can observe and what we can predict. And math doesn't deal with infinities very well, right? Infinity is not just a number that you can plug into an equation and get a meaningful answer out of. So our current understanding of physics doesn't really let us understand what what was going on immediately at time equals zero, right at the Big Bang. But a tiny fraction of a second after the Big Bang, at 10 to the negative 43 seconds after the Big Bang, basically the smallest unit of time that our current understanding of physics lets us handle is 10 to the negative 43 seconds. So, at time equals zero, the universe was infinitely hot. And what was that like? It doesn't mean much, right? Whatever you could try to say, it doesn't mean a whole lot. But if you let time go forward by the tiniest unit, 10 to the negative 43 seconds, then the universe has cooled off to, instead of being infinitely hot, it's now only ridiculously hot. It's 10 to the 32 Kelvin. Right? So that's where the story of the Big Bang begins. When the universe is 10 to the negative 43 seconds old, and the universe is 10 to the 32 Kelvin. Ridiculously hot, but not infinitely hot. So now we have a number that we can plug into equations and say, well, what was that like? And then as the universe expanded, right, as you let time go forward, the universe expands and gets bigger and bigger and bigger. And what happens to a gas and energy when you let it expand? It cools off. So the universe cooled off from ridiculously hot to cooler and cooler and cooler and cooler and cooler until it's here we are today, right? We today are at 10 to the 17, around 10 to the 17 seconds since the Big Bang, and the universe has cooled off to being fairly cool. We would like to know what was going on right at the Big Bang, right? It's not enough. It's a lot to say, well, we know what happened 10 to the negative 43 seconds after the Big Bang, but we would like to know, how did the Big Bang happen in the first place, right? What triggered the Big Bang? Are Big Bangs common or are they rare, right? I mean, to the best of our knowledge, the Big Bang, to the best of our knowledge, a second Big Bang has not happened since our Big Bang happened. You'd think we would have noticed. You'd think. But are they unique, right? Is the creation of our universe unique? Or maybe the conditions in space and time and heat and energy allow them to happen more than just once. And for that, we would like to know what the universe was like closer. Like I was saying, our current understanding of physics allows us to go all the way back to when the universe was only a tiny, tiny, tiny fraction of a second old. And when the universe was very small and ridiculously hot. And that's a lot. But we don't know what the universe was like right at the beginning, right at time equals 0. In order to answer that question, we need better physics. Right? We need new theories, we need better theories of physics that can get us closer to what happened before 10 to the negative 43 seconds. And people are working on that now. And a lot of the new and weird theories of physics that you'll occasionally hear about in the news, new, modern, cutting-edge, experimental theories of the universe. This is one of the problems that some of those new theories are trying to answer. We're not there yet, but people are working on it. So, this is another one of those things that we're going to be hearing about every once in a while for the rest of our lives, because this is a problem of like, how did we get here, right? Why are we here? How did this all happen? And by this I mean like capital E, everything. How did everything in the universe come to be? Why is our universe the way that it is? Why is our universe not some other way? This goes to those very beginning questions that we're going to give some answers to today in this lecture. But some of these big cosmic questions, we need better theories of physics to be able to answer. So keep an ear out now and then. We'll hear about some people trying to attempt it for the rest of our lives, hopefully. The thing is, when the universe is 10 to the 32 Kelvin, there's one thing that we've noticed for a long time in particle accelerators and in high energy physics, and that is when you take matter and energy and make them very high energy, when you take particles and you make them really hot, matter and energy don't look that different. they look identical. At that point, matter and energy, when the universe was brand new, 10 to the negative 43 seconds after the Big Bang, there were no particles yet. Everything was just fields of energy floating around the universe. Pure energy. When the universe was 10 to the negative 38 seconds old, the universe had cooled off to only 10 to the 29 Kelvin. And this is where the pure energy starts to take different forms, right? Electromagnetism and the weak nuclear force start behaving differently at these temperatures. And at this point, particles start showing up, right? Because because remember what we said before, right? The weak nuclear force is the force of nature that is responsible for giving particles their identity, right? And the electromagnetic force is the force that governs how charged particles behave. So once electromagnetism, and the weak force start differentiating and behaving differently, then the weak force can allow two photons, let's say, two photons can collide together and get turned into an electron and a positron. Remember, positrons are just antimatter electrons, right? This is another example of E equals mc squared, right? E equals mc squared is the relationship between energy and mass, right? If you take some particles' mass and multiply by the speed of light squared, that tells you how much energy it takes, or how much energy is contained in that mass. So you take a couple of gamma rays and smash them into each other, and all that energy from the gamma rays gets turned into the mass of the electron and the positron. But matter and antimatter destroy each other, right? When you create electrons and anti-electrons, they're attracted to each other. One's negative, one's positive. They're going to be attracted to each other. When that positive positron and that negative electron, when they collide, matter and antimatter annihilate each other, and they turn all that mass back into energy. So this is happening constantly, right? When the universe is 10 to the negative 38 seconds old, the universe is still tiny and insanely dense, and photons and electrons are constantly turning into each other. Two photons turn into an electron and an anti-electron. The electron and the anti-electron smash back into each other and turn back into two photons, which can turn back into electrons again. This is happening over and over and over and over and over again. Energy and matter are constantly turning into each other over and over and over and over and over again. Rapidly. This keeps happening for about a millisecond. By the time the universe is 1 millisecond old, the universe has cooled off to a chilly trillion degrees Kelvin. And at 10 to the 12 Kelvin, now at 10 to the 12 Kelvin, all four of the fundamental forces are now behaving the way we know today, right? Gravity, electromagnetism, the strong force, the weak force, they've all settled down, and the forces of nature as we know them today are behaving back then the same way they do today. Right? So now that you've got the strong force is the force that governs quarks and protons and neutrons, right? And so now that the strong force is doing its thing, you can have quarks bind together into protons, and protons and neutrons, again, this is a trillion Kelvin. So what happens when you've got a bunch of protons and neutrons flying around at a trillion Kelvin? Well, they're going to collide and they're going to fuse. And so a proton by itself, remember, what's a proton by itself? A proton by itself is a hydrogen nucleus. But you can take a proton and a neutron and fuse them and make a heavier isotope of hydrogen, which we call deuterium. We talked about that when we talked about proton-proton chain fusion, right? And then a couple of protons and a neutron can collide with each other and make helium-3, or two protons and two neutrons can smash into each other and make helium-4. Or you can take a few protons and a few neutrons and smash them into each other and make something like lithium-7. That's about it, though. Remember, in order to take light elements and fuse them into heavier elements, what does it take? What does it take to have nuclear fusion? It takes heat. They got to be hot and they got to be dense enough to fuse, right? Well, the universe is rapidly expanding and rapidly cooling off. So the time for this nuclear fusion to happen is rapidly diminishing. This era of hydrogen fusing into helium and a little bit of lithium lasts for 3 minutes. For the very first 3 minutes of the universe, particles are smashing into each other fast and furious, and hydrogen is, I mean, not all the hydrogen, but a lot of that hydrogen is smashing into protons and neutrons and fusing into helium for 3 minutes. And those first 3 minutes, in those first 3 minutes, the universe is quickly expanding, quickly cooling off, and after 3 minutes, the universe cools off and it dropped below 10 million Kelvin. Right? And once the universe, we can see that in this model right here, right? After the universe was, this is insane, right? Look at this graph. Let's see. 10 to the 0 is right here, right? What is 10 to the 0 power? It's 1. So this is the universe when the universe was 1 second old. This entire left 2/3, 3/4 of this graph is the very first second of the universe. From the Big Bang to when the universe was 1 second old, the universe went from this hot to this hot. Right? This is what I mean when the universe was cooling off rapidly. When the universe was 100 seconds old, the universe cooled off to, yeah, that's about right. Yeah, like 10 million Kelvin. Right? Remember, 10 million Kelvin is the magic number where hydrogen fusion stops. Or if you heat up above 10 million Kelvin, that's when hydrogen fusion starts. Right? So, after 3 minutes, the universe cools off to below 10 million Kelvin. 10 million Kelvin is still hot, but not hot enough for fusion. At the end of that first 3 minutes, about 1/4 of the hydrogen had fused into helium. The other 3/4 is still hydrogen. Right? The universe was only hot enough for fusion for that first 3 minutes, and in that 3 minutes, the universe was hot enough, long enough for 25% of the universe to end up being helium. 75% of the universe was still hydrogen, and a tiny, tiny, tiny sliver of the universe was a little bit of lithium, but that's it. Right? Aside from this very, very tiny fraction of lithium, there were no metals in the universe yet. This is the second big line of evidence for the Big Bang. Right? The idea that our universe began with a hot, dense Big Bang logically leads to a universe after that 3 minutes where the universe is 75% hydrogen, 25% helium. And we can ignore the lithium because it's basically, it's effectively zero. It's not zero, but it's almost zero. That ratio, that has been our universe for pretty much the whole history thereafter. Right? When you look at the oldest stars, what are they made of? 75% hydrogen, 25% helium, very tiny, tiny metallicity. When you look at middle-aged stars, when you look at stars from 10 billion years ago, what are they made of? 75% hydrogen, 25% helium, a little more metals. When you look at population 1 stars like the sun, they're basically the same. They're basically 75% hydrogen, 25% helium, a little bit more metals. Right? Every other element in the periodic table was created in the cores of stars and during the deaths of stars. But the helium, right? Most of the helium in the universe and all of the hydrogen in the universe was created in the Big Bang. And it's been there, it's been like that ever since. The chemical history of our universe is a separate piece of evidence that directly follows from the Big Bang Theory. If the Big Bang hadn't happened, or if the Big Bang had happened differently, the whole history of stars and galaxies would have been wildly different. And stars like the sun and planets like Earth and people like us wouldn't be here. So this doesn't depend on the Hubble redshift, right? This doesn't depend on the expansion of the universe. This is a totally separate line of evidence that comes to the same conclusion, a hot, dense Big Bang. All right. So, when the universe was 3 minutes old, the universe was kept on expanding. It was 10 million Kelvin, and it just kept on expanding and cooling off. For the next 380,000 years, our universe was this hot, thick fog. Right? The universe was still hot. It was ionized. The whole universe was filled with this ionized hydrogen-helium plasma. And I say fog because it was opaque. Light couldn't travel through the universe yet. There was a lot of light. There was a lot of photons flying around everywhere. They just couldn't travel very far because every photon would travel a short distance and then run into a proton, a helium nucleus, an electron, all the charged particles that were flying around everywhere. Our universe was filled with these hot charged particles and then all the photons ricocheting around them. In order to form an atom, right? What is an atom made of? An atom is made of a nucleus with electrons around it. At this point, the universe was too hot. Too hot for electrons to get bound to hydrogen or helium nuclei. That's what made the gas opaque. And so slowly, over 380,000 years, the universe cooled off and cooled off and cooled off until the universe dropped to 3,000 Kelvin. That's why from 10 million to 3,000 is a big drop. That's why it took 300,000 years to happen. But then finally, right, the universe was filled with this hot, dense fog for 380,000 years until finally the temperature dropped to below 3,000 Kelvin. And below 3,000 Kelvin, everything had cooled off enough so that the nuclei could grab onto the electrons. And those electrons all got bound around a nucleus, and then the universe turned from this hot plasma into a neutral gas, like the air you're breathing right now, right? I'm assuming you're one of my students this semester and not a robot from the far future who doesn't breathe air. I'm assuming, but go with me here. Right? The air around you right now is transparent. Why? Because it's neutral. All of the electrons are bound around their atoms, and when all of the protons and electrons are bound together, it's a lot easier for light to travel through that gas. And so quickly after, when the universe was 380,000 years old, the universe fairly rapidly, once the universe cooled off, below 3000 Kelvin, it quickly neutralized. The electrons all got snatched up in their atoms, and the universe went from being an opaque gas to a transparent gas. And then it's as if the fog cleared. The fog cleared, and the universe became transparent. Light could travel through the universe for the very first time in history. Except there were no stars yet, right? The universe was just a transparent gas with light that now, for the first time, could fly through the gas out through space. The original work on this was done by Ralph Alper and George Gamow in the 40s, where basically they said, well, what was the universe like back then, right? When the universe neutralized for the very first time. Well, what would that light have been like? Well, it would have basically been this afterglow, right? The very first light that got released once the universe turned into a transparent gas. This would have been the very first light that was allowed to fly through space. It would have been this, essentially this afterglow from the Big Bang. It's not exactly the light from the Big Bang, because the light from the Big Bang was trapped in the universe and we can't see it now. But the very first light that got released when the universe dropped below 3000 Kelvin, that's something we could still see. Alper and Gamow predicted this light should still be flying through the universe, right? Light has been able to travel through the universe ever since then, and so it should be out there for us to see. And what would that light look like? Well, the light, this afterglow, would have been given off when the universe was hot and dense. And what kind of light does a hot, dense object give off? It gives off a blackbody spectrum. So they basically predicted that there should be this glow, this afterglow left over from the Big Bang when the universe was only 380,000 years old, and it should be a blackbody, right? Because it was given off by when all of the gas in the universe was hot and dense. Now, this is here the math is very convenient, because 3000 Kelvin is also the temperature of the coolest stars. So a star gives off a blackbody spectrum. What kind of light is most prominent in a really cool star? What color is a cool star? It's red. So basically, the very first light that got shone into the universe, shined into the universe, would have looked like a red star. But that was a long time ago, and the redshift of the universe, the expansion of space-time, would have redshifted that light so that it doesn't look red anymore. It has been stretched, all of those photons, because space has expanded a lot since the universe was 300,000 years old. So all that red light would have been stretched to be radio waves at this point. So basically, Alper and Gamow write a paper that says, hey, there should be this afterglow left over from the Big Bang, and it should be in the radio spectrum. They should be radio waves now. They write this paper, and it doesn't go anywhere. Nobody reads it. People read it, but nobody pays that much attention. Why? Because nobody ever saw the afterglow, right? People read that paper and go, neat idea, but where's the light? Flash forward to 1965, and Arno Penzias and Robert Wilson, this is Penzias, here's Wilson, they're working at Bell Labs in New Jersey, and they're building this new radio telescope, which is what's behind them here, right? Here's the opening of the radio telescope. The radio waves come in here. They bounce off this diagonal sheet. Basically, this diagonal sheet in the back acts as a mirror, and so the radio waves come in here, bounce off here. They bounce around inside this horn, and the horn concentrates the radio waves until they reach the receiver, which is essentially the camera in this shed. They build this new radio telescope and they test it out. And one weird thing that they find as they're testing out their telescope is that there's a glow everywhere they look. Whether they're looking at a galaxy or a star or empty sky where there should be no radio waves at all, they see this afterglow. Or I should say, they see some glow. They see some radio waves, and they can't explain where these radio waves are coming from. And then they contact some friends, and they say, "Hey, I'm getting this weird radio signal in my telescope. Where could it be coming from?" And one of their friends, Robert Dicke, says, I seem to remember a paper from Gamov a few years ago. Maybe that's what it is." Basically, what Penzias and Wilson discovered, more or less accidentally, is they discovered the afterglow from the Big Bang. What we call this these days, we call this the cosmic microwave background radiation. It's cosmic because it's everywhere in the universe, right? This light was released from everywhere in the universe at the same time, and it was released in all directions. And if this light is coming from all directions and flying in all directions, what that basically means is it's everywhere in the sky. Every direction you can look, every direction on the entire celestial sphere, this light is coming to us because it was released by everywhere in the universe all at the same time. So that's why it's called a background radiation, right? It's cosmic because it's happening everywhere in the universe. Microwave because the light is in the microwave part of the radio spectrum. Background because it's in the background of all the pictures, right? Behind every picture in astronomy, frankly, every picture you've ever taken with a camera, right? Behind the stars, behind the galaxies, the oldest light in the universe, the very first light that was released into the universe, is now this cosmic microwave background. So this is a big discovery, right? Literally the very first light that emitted into the universe after the Big Bang. This is a big deal. The problem is, of course, that you got to look around the whole sky, and in order to map the whole sky, the Earth is in the way, so that's inconvenient. The very first mission to map the cosmic microwave background in detail was this mission called COBE in the early 90s, and here's the spectrum, right? Take the spectrum. This is brightness versus frequency. We're used to dealing with spectra in terms of brightness versus wavelength, but they're essentially the same thing. What do you notice? It's smooth. It is a smooth, continuous graph. It is a perfect black body. It's a perfect black body spectrum. Why? Because this light was given off by all the matter in the universe, all at the same time, when the universe was 380,000 years old. Back then, there was no low density gas to be giving off emission lines or absorption lines. The entire universe was a perfect black body. The entirety of the universe was a perfect, hot, dense object giving off a perfect black body spectrum. And that's the light that we see today. The light from the cosmic microwave background is not only everywhere, it's the same temperature everywhere, because again, this light was given off by the universe when the universe was all the same temperature, all at the same time, which means everywhere you can look in the sky, the temperature of the universe in all directions everywhere was all the same. And the universe since then has cooled off to the point that the universe today is about 2.7 Kelvin. Everywhere in the universe, the emptiest, blackest, coldest part of the universe still has heat flying through it in the form of light left over from the Big Bang. So that everywhere in the universe is not absolute zero. It's 2.7 Kelvin above absolute zero, because the universe started out hot and dense, and the universe has been expanding and cooling off ever since, but the universe hasn't completely cooled off yet. The universe has cooled off to the point that it's still 2.7 Kelvin now. So this is line of evidence number 3. A separate observation, the discovery of the cosmic microwave background radiation, the discovery of the light left over from the Big Bang, is a third major line of evidence that says, how can this happen? Why is this light everywhere in all directions in space, everywhere in the universe? And the answer is because, well, back then the universe was smaller, denser, hotter, and then it kept on expanding. And I mean, it's the same in all directions, right? This is, I mean, I'm being a little cheeky with this cartoon, but I've been using that word a lot this week. But I'm being a little tongue in cheek here. But what am I? I guess that means the same thing. Anyway, pardon me. What is this graphic? This is essentially a map of the sky, right? Take the entire celestial sphere and unroll it, flatten it out like a map. So here's the entire celestial sphere as seen from Earth, right? It looks the same in all directions. Meaning what? Meaning that the universe is the same temperature in all directions, right? Every direction we could look, north, south, around the celestial equator, right? Everywhere we look, the universe is the same temperature. Why? Because the universe was the same temperature back then. Because the universe started out hot and dense, right? That's why I said in the previous slide that this observation confirms the Big Bang precisely, right? How do you explain why the universe is the same temperature in all directions? Well, because all directions were the same direction back then. Everywhere in space was the same point in space at the Big Bang before the expansion started. And that's why, even after 13.8 billion years, it's all the same temperature still. Almost. Right? Actually, there are tiny little temperature variations. So these are actual maps, not my little silly cartoon. This is the original map from the COBE satellite in the early 90s. This is a higher resolution. This is a clearer resolution map made by the WMAP satellite much more recently in the last several years. These are maps of little hot spots and cold spots in the cosmic microwave background. The universe is almost the same temperature. That last digit there is where it differs. So the universe is 2.72 Kelvin in all directions. If you take that last little digit, if you take that millikelvin and turn up the contrast so that the hot and cold spots stand out, you get something like this. Now, here it is in a little bigger to tell the details. It's worth noting these maps they're not black body colors, they're Fawcett colors, by which I mean these maps are color-coded so that red means hot and blue means cold, which seems like the opposite in astronomy, right? But these are all radio waves, so we can color-code it any way we want to. So what are we looking at here? Little hot spots and little cold spots. What would cause the universe in that direction to be a little hotter or a little colder? And the answer is galaxies, right? The collapse of gas. Early on in the universe, the gas was starting to clump up and collapse, and then eventually those collapsing clumps of gas would collapse and form the very first stars and the very first galaxies and the very first clusters of galaxies. That's what we're looking at here. What we're looking at here are these little, I mean, well, they're the size of clusters of galaxies, so they're big, but they're little in the grand scheme of things. This is basically the baby pictures of the universe, where the gas that filled the universe was hot and dense. It was a perfect black body, but there were areas where the gas was already starting to clump up and collapse, and eventually would, millions and millions and millions of years after this light got created, the gas would eventually collapse and form the first superclusters of galaxies. This is an important image. This is an important measurement, because this is basically an imprint of the sizes of galaxies and the sizes of clusters. Right? If we zoom in here, right, you can look at this in some more detail, and you can see the sizes of the hot spots and the sizes of the cold spots mean, well, in this direction, why is this area hotter? Because there was more matter here, and that matter collapsed, heated up, gave off, it gave off a little hotter black body curve. This area, there was less gas over here, and so it was a little cooler, and therefore it gave off a cooler black body spectrum. Today, if you look in these parts of the sky, there's more galaxies over here and less galaxies over here. Over here is where the clusters of galaxies are happening. Over here are the voids in between galaxies, or in between clusters. In the last video, when we were talking about dark matter and the simulations to simulate our universe and how our universe evolved, right? The simulations that we've tried to do to say, what kind of a universe do we live in, such that we create a simulation that reproduces the universe that we live in, with the clusters of galaxies and the voids between galaxies that we actually see. This is one of the big observations that we're trying to explain with those simulations, to say, why are these hot spots this size and this temperature? Why are the cold spots this size and this temperature? All of that has to do with the expansion of the universe, so Hubble's constant. It has to do with how the expansion rate of the universe has changed, in other words, dark energy, right? And then, gravity, dark matter, and how dark matter has pulled the gas together to form galaxies. What caused the gas to collapse here and form stars and galaxies? I mean, one of the big answers is dark matter. So when I say this image is important, what I mean is this is a big piece of evidence for what the universe was like when it was only 380,000 years old. And this evidence, these baby pictures of the universe, this is the kind of evidence that we're trying to explain when we figure out what is dark matter, what is dark energy, right? Dark matter wants to make the gas collapse and form galaxies. Dark energy wants to push everything apart so that the gas spreads out, thins out, and cools off. Any good idea for what the dark energy and the dark matter could be is going to have to explain, okay, so why are there this many hot spots, and why are they this hot, and why are they this many? If we lived in a universe with even more dark matter, you would see hotter hot spots. If we lived in a universe with even more dark energy, the dark energy would have spread out the universe faster, and you'd have cooler hot spots. if there are scientists trying to, I mean, I shouldn't say if, there are scientists trying to explain the dark matter and the dark energy, and if someone has a good idea for what the dark matter or dark energy could be, you would look at that explanation and say, oh, neat idea, but is there enough of that in the universe? Is that in the universe in all the right places to explain the hot spots and cold spots in the early universe? If your idea can't explain these, then your explanation doesn't match the universe we actually live in. All right. So, the first 7 years of data got released by the WMAP satellite in 2010. And basically, this is another way to put a fine point on what I was saying a minute ago. This is another way of measuring the Hubble constant. Right? If we understand dark energy, we can understand, okay, why is the Hubble constant what it is? Why is it 71 or 69 or 68 or 75 or 100 or 50 or whatever, right? The Hubble constant has to, I should say, the Hubble constant influenced the size and the number of the hotspots. And so rather than just measuring the redshift and the distances to galaxies, like we were doing before, right? Like we did before, to say, well, find white dwarf supernova, use those white dwarf supernova to get the distance to the galaxies, and then use the distance and the velocity of the galaxy to figure out what the Hubble constant must be. That's one way, and it's a very good way of measuring the Hubble constant. The reason today why we have such confidence in what the Hubble constant is that we have a second way of measuring the Hubble constant. The second method for measuring the Hubble constant is to look at the cosmic microwave background and say, well, how fast must the universe be expanding to explain the hot spots and the cold spots? And when you do that, the answer comes out to be 70.2, which is pretty darn close, right? That agrees fairly well with the Hubble constant you get from a white dwarf supernova, right? There's the universe we live in. Right? This is a graphic showing sort of the evolution of the universe from the beginning to today, to the universe as we see it in the WMAP. This is an illustration of the WMAP satellite. Right? The Big Bang happened. The universe was hot and dense, and we can't see it. The other reason why we can't know for sure what was going on during the Big Bang is that we can't see the Big Bang. Right? Everything that was happening right during the Big Bang has been hidden from us because the universe was opaque back then. The light from the Big Bang, we can't see it in the universe because that light was not released until the universe neutralized 300,000 years later. This is the original light, right? When you're looking through a telescope and you look nearby, you'll see stars. You look far away, you'll see nearby galaxies. When you look even further away, you'll see far away galaxies. When you look before that, you'll see little tiny early galaxies that are glowing because they're glowing with the light of the very first stars. Right? That's the universe that we see in optical telescopes. Before the very first stars showed up, the universe was dark. In astrophysics, we actually call this the Dark Ages because there was nothing giving off light back then. Right? There were no stars. There were no galaxies. The only light in the universe at this point in history was the light from the cosmic microwave background shining through an otherwise transparent gas of a universe. Right? And then before that, that's the light in the background. Right? Behind the galaxies, behind the nearby galaxies, behind the stars, in the background of every image, the oldest, most original light in the universe that's still around is the CMB, the cosmic microwave background. This is very much a frontier of knowledge. It's very hard to see the very first stars in the very first galaxies because A, they're very far away, and B, well, okay, I'm changing my list here. A, they're very far away. B, that light has been so redshifted that it's not visible light anymore. It's infrared and radio waves. And C, all the galaxies were small, right? In order to form big galaxies, you need to eat up a lot of small galaxies. You need galaxies to merge and crash into each other to form big galaxies, right? Before there were big galaxies, there was just a bunch of small galaxies, and a bunch of little clusters of stars that hadn't crashed into each other yet. And so the study of the early stars and the early galaxies in the early universe is... it's not that we know nothing. We know a lot, but we certainly have a lot of questions left. We want to get better pictures of the very first stars that formed, the very first generation of stars in the universe that formed after the Dark Ages. This is one of the main missions of the James Webb Space Telescope. The JWST was created. One of the reasons why it was built is to be able to see those faraway stars and galaxies, because it's an infrared telescope, right? That light from those first stars used to be visible light, but now it's been redshifted all the way into the infrared. So if you have an infrared telescope, you can see what used to be blue. What used to be blue light, now it's infrared. So build an infrared telescope with an infrared camera, and you can see these blue stars. And that's why we launched the JWST, and knock on wood, everything goes well, and it'll be running great for years to come.